Hi everyone, this is Dr. Nak, and today we're going to talk about transformation of functions. So what we're going to do is, giving a basic graph, we're going to shift that up and down, left and right. We can even flip it over, or you can stretch it out or shrink it. So those of you who like graphing, this is the section for you. Before we get into all the fun, first we're going to have to learn the definitions. So just to save some time, I already wrote down the definition here. So let's first go with the vertical shift. What is it? Well, that's moving the graph up or down. Horizontal shift means that you're going to be moving the graph right or left. Now, how do we express that by using a function notation? So I wrote down here more formally. Number one, if a positive real number k is added to the output of the function y equals f of x, the graph of y equals f of x plus k. So our f of x is the given graph, and then if I add k units to it, that is the graph of f shifted vertically up k units. And y equals f of x minus k is the graph of f shifted vertically down k units. So you can think of y equals f of x plus or minus k as like a formula how to shift the graph up and down. Now let's talk about the horizontal shift. So I put it under number 2. If the argument of x of a function f is replaced by x minus h, where x is positive, then the graph of the new function y equals f of x minus h is the graph of f shifted horizontally right h units. And y equals f of x plus h is the graph of f shifted horizontally left h units. So again, you can think of these two functions are maybe the formulas how to shift the given graph right or left. Okay, so let's do some examples. So example 1, use the graph of f of x equals x squared to obtain the graph of g of x, which is f of x minus 2. Find the domain and the range of g of x. Okay, so let's first graph y equals x squared. And you might want to start memorizing the basic graphs. Basic graph means x squared, y equals to x, y equals to 1 over x, and so forth. But don't worry, I've already summarized everything for you, so we'll talk about that at the end. So if you're not too comfortable, or if you forgot what the y equals x squared looks like, it is not the end of the world. We can always make ourselves a chart. So let me start out with like maybe -2, -1, 0, 1, 2. So those are the x values. So y values is going to be -2 whole quantity squared, so which is 4, and -1 squared, which is 1, and then 0 squared is 0, 1 squared is 1, and then 2 squared is 4. So let's use these points to graph y equals x squared. And here it is. All I did was just plot at some point. So this is y equals x squared. So sometimes we call this graph the mother graph. That's what I usually call it. But anyways, let's take a look at the our g of x, because that's the graph that we want to draw. So our g of x is f of x, which is what we just graphed, and then minus 2. Okay, so what does it mean? Well, that means that we're going to have to shift our mother graph 2 units downward. So when x is 0 and y is 0, which is 0, 0, we're going to shift that point down 2 units down. So that will be this point right here. So in this case, we're going to have 0, -2. I don't know if you can see that color. Maybe this is a bad color. But anyways, let's just keep going. Okay, so now let's take our point. What is that? -1, 1, and we're going to shift this point 2 units downward. So that will be here, which is -1, -1. All right, so then, you know what? Let's just keep doing this. So now let's go with this point right here. So right now, what is that? -2, comma 4. Is that the point? Yep. So now we're gonna move this point 2 units down. So we're gonna get this point here, which is, what does it look like? -2, comma 2. And let's just do the same thing on the right hand side of the graph. So this point, I'm gonna move it 2 units down. So this will be 1 comma -1. So that's this point right here. And then this point here, we're gonna have to move this point 2 units down. So that will be here. So what is that? So that's 2 comma 2, is that right? Okay, now all you have to do is just connect those dots and redraw the graph. Now here's another way to think of it. Remember, y equals f of x, right? So our g of x is y minus 2. So that's telling you is, so here's the chart for the mother graph, right? Your x values is not going to change. But in order for us to get g of x, all you have to do is take each of the y values and then subtract by 2. So just to show you that, let me just remake the chart. So again, all I did here was just copy and pasted this chart, which is that mother graph, right? So what I was telling you earlier is that in order for us to graph g of x, all you have to do is take each of the y values and then subtract that by 2. So here, I'm just gonna go -2, -2, -2, -2, and a -2. And the new y value is gonna be 2, and then -1, -2, -1, and a 2. So this means that our new graph, g of x, what do we need to plot is when x is -2, y is 2. When x is -1, y is -1, and then we're gonna have a 0, comma -2, 1, comma -1, and then 2, comma 2, which matches up with the way we drew the graph by just shifting each of the points 2 units downward. All right, now let's not forget the second part of the question. Find the domain on a range. All right, so let me just, where can I write it? So let's go with the domain of g. Okay, so what do you think? So domain of g, I claim that it's all real numbers because, first of all, y equals x squared is a polynomial. And then remember, we talked about this. Domain of all polynomials are all real numbers. Or you can think of it as, okay, where's the function defined along the x-axis? Well, this graph is going to keep going and going and going and going, and then going this way as well. So it's going to be from -infinity to infinity. So I'm going to say domain of g is set of all x such that x is all real numbers. Or in an interval notation, this will be -infinity to infinity. All right, now let's go with the range. All right, so look at our new graph that's drawn in green. So let me see. When you look at the range, you want to look at the graph from bottom upward. So from the bottom upward, right, where does the graph begin? What y value? Well, our y value starts at -2, and then it goes all the way up to infinity. So the range of f is going to be, I'm running out of room, set of all y values such that all the y values must be greater or equal to -2. Or in an interval notation, you're going to have, close bracket, -2 all the way up to infinity. So this is the domain and the range of our function g of x. All right, now let's do another example, example 2, a function f of x given in the table below. Create a table for the function g of x equals f of x plus 3. So what is the difference between example 1 and example 2 is that in example 1, our function was given to us. It was f of x equals to x squared. But here, the only thing that you're given is the chart of the mother graph. So here are the x values, and so this is y equals f of x. Now let's create our g of x. But before we compute it, those of you who's more of a visual learner, let me just plot those points. Okay, so the mother graph, the first ordered pair is 2, 1. So that will be here. Is that 2, 1? Yep. And then 4, 3. So you got 4, 3. And then 6, 7. And then 8, 11. So I'm not quite sure if I should connect all those dots or not, but these are the points that you're given. And then our g of x is f of x, and then you add 3, right? So in this case, all you have to do is this. We're given f of x here, right? And then you're going to have to add 3. And so that's going to be the new values that you're going to be listing on the third column. So here, let's just do it the same way as we did in example 1. So we're going to go plus 3, plus 3, plus 3, plus 3. So then what do we get? New y values are going to be 4, 6, 10, and then 14. Did I add that right? So the new ordered pair is going to be, so let me just change the color for a little bit. So this is going to be 2, 4, and then 4, 6, 6, 10, and then 8, 14. All right, so let's see. So 2, 4, 1, 2, 3, 4. So that's our 2, 4. And then 4, 6. And then, what is it? Now, what's the next one? 6, 10. Oh no, I'm going to run out of room. So 8, 14. So you're going to have 8, I don't know, 14, like maybe right here. So now let's just make sure that this makes sense. So the blue dots are coming from the mother graph. So let's see. From this point, which was, what was it, 2, 1, do we go 3 units above? Yes. And distance from here to here is 3, and then 3, and then 3. So it looks correct. So this chart is correct. So basically for the vertical shift, your x stays the same. But only thing that's going to change is the y value. So change y value. So how should I write? The x stays the same, y changes. Does that make sense? All right, but anyways, let's look at another example. So here's example 3. Function f of x is given in the table below. Create a table for the function g of x equals f of x minus 3. So first, given f of x minus 3, you need to recognize right away that this is going to be a horizontal shift. Furthermore, you're going to have to move it 3 units to the right side, not the left, just because of that minus. Basically, take the opposite of it. So shift 3 units to the right. Okay, so let's just think about this a little bit. Okay, so suppose this is our mother graph. Suppose it looks something like this happy face, a parabola, I should say more formally. And you're going to be moving this graph horizontally. So that means that you're going to be taking this graph and then you could either go left or the right. So what value does it change? Well, y values should stay the same, right? But the only thing that's changing is the x values because you're shifting this graph to the right or to the left, right? So all the y values stays the same, but the x values changes. So keep that in mind and let's make a chart for g of x. So I'm going to show you how to do this problem in 2 different ways. So the way that I'm doing is pretty much my own way because I know that if I shift the graph horizontally, the only values that's going to get changed are the x values and the y value stays the same. So as long as you know that, then you just keep this original f of x as is. So that's going to be the y values for your g of x. And then all you have to do is change the values for x. Okay, now how much are you going to change the value of x is this? Well, look at it. You already know that this is a horizontal shift 3 units to the right, correct? So here, what you need to do is add 3 to each values of x, and that's going to become the new values for x for our function g of x. So if I did it that way, then I'm just going to keep this 1, 3, 7, 11, and then all I have to do is add 3 to each of the value of x from the mother graph. So this is going to be, let's see, let me just write 2, 4, 6, 8, and I'm going to add 3. So the new values are going to be 5, 7, 9, and then 11. So that means that our graph g of x, that's going to go through when x is 5, y is 1. And when x is 7, y is 3, and then x is 9, y is 7. And when x is 11, and then y is 11. Okay, oops, I forgot to plot the points for the mother graph. So let me just do that real quick. So 2, 1, so you got 2, 1, 4, 3, 6, 7, and then 8, 11. All right, now let's plot the new points, which is 5, 1, and then 7, 3. Notice that the y values are staying the same, right? And then 9, 7, 11, 11. So our blue dots are from f of x, and then those pink dots are g of x. Now let's see, does it make sense? I think it does, because our conclusion was what? Taking the mother graph, and then we're going to move that 3 units to the right. So let's see. So here is the point from the mother graph. 3 units to the right. Yes, it makes sense. So this is called the horizontal shift. So here, this point, if I add 3 to it, I can get to here, or I should say distance from here to here is 3, and from here to here is 3. So every point got shifted 3 units to the right. So this does make sense. All right, so let me show you what the book does, your textbook. So what I did here was I just drew the same chart. So this was the mother graph given in the way that we just did. And let me write down what our g of x is. So g of x is f of x minus 3. Then let me make a similar chart for our function g of x. All right, are we ready? So let's take a look at this. Okay, so what does this mean? So this is when x is 2, our y is 1. Or this is same thing as f of 2 equals to 1. Isn't that how it translates? Now, how the textbook does it is this. Look at our function g, right? That's f of x minus 3. So what we need to do is we need to try to rewrite f of 2 by using f of x minus 3. So you're going to have to write the equivalent expression by using f of x minus 3. Meaning this, so if I have f of x minus 3 to be 1, right? You want to match up this argument of f and this argument of f. So the question is, what is the value of x so that when I plug that x values in, I'm going to get 2 back? Well, that will be x equals to 5, correct? So the way they do it is I'm going to rewrite it as f of 5 minus 3 equals to 1. So that gives us that our x is 5. So that's why they write it as x is 5 and then our y is 1. Now they do the same thing for this ordered pair. So let me just bring it over here. So when x is 4, y is 3. So this is same thing as f of 4 equals to 3. Now let's try to rewrite f of 4 by using f of x minus 3. And I'm going to set the right hand side equal to 3. So what number do I need here so that if I subtract 3 from this number, I'm going to get 4? Well, that number is 7, right? So this portion here, let me just do it the same way. F of 7 minus 3 will give us 4. So that means that our x value has to be 7. So now let me rewrite it as 7, and then y value stays the same, which is 3. Does that make sense? And then let me take 6 comma 7. Let's do the same thing. So we have a 6 comma 7. So that means that f of 6 must equal to 7. All right, so now we need to rewrite this as f of x minus 3 equals to 7. So the question is, what numbers do I need for x in order to become 6? If I subtract this number minus 3, it's going to equal to 6. That will be 9. So we could rewrite it as f of 9 minus 3 equals to 7. That means that x values has to be 9. And then the y value is 7. Okay, and then let's just finish it up. So now let's take 8 comma 11. Let me just go over here. So we have 8 comma 11. So that means f of 8 equals to 11. Now I'm going to rewrite it as f of x minus 3 equals to 11. And so what is that magical number? I believe x has to be 11. So f of 11 minus 3 equals to 11. So is 11 minus 3, does it equal to 8? Yes, it does. So that means that your x has to be 11 now. So that's why we're going to have a 11, and then our y value is 11. And so that's exactly the same answer that we got before. Okay, so either way, either method is okay. Stick with the way that you feel more comfortable doing. All right, but as long as if you know that if you have to do the horizontal shift, know that only the x values change and then y value stays the same. So I'm gonna write that out. So horizontal shift. So in this case, your x value changes, but the y values stays the same. All right. Okay, so there you have it. All right, so let's take a look at example 4. Use the graph of f of x equals square root of x to obtain the graph of g of x equals x plus 4. Find the domain and the range of g of x. So if you want to try this on your own, please pause the video and try it. But I'm just gonna keep going. So our mother graph is f of x equals to square root of x, right? And then our g of x is square root of x plus 4. So I can rewrite it as f of x plus 4. So that's square root of x plus 4. But thing is, this is precisely our g of x. So what does this mean? Given f of x, I'm going to have f of x plus 4. So do you see that this is going to be a horizontal shift? Which way does it go? 4 units to the left. So all you have to do is draw the mother graph of square root of x and then horizontal shift. Do you remember what value changes? Is that the x value or is it the y value? Yes, x values changes, but the y value stays the same. All right, so let me just write it out. I'm going to write it as horizontal shift means that x values changes, but the y values stays the same. Now, you don't need to make a chart for this because the problem didn't ask you to make a chart, but let's just make the chart just for heck of it. So let's go with x and then our f of x, which is the square root of x. Okay, so let's pick some nice values for x. Okay, so I'm going to work on the mother graph first. So 0 is nice because square root of 0 is just 0, right? And then which one is the next nice number? 4, because then square root of 4 is going to give us 2. And then next one is 9, because square root of 9 is going to give us 3. Do you see what I'm doing? I'm trying to pick a nice number. 6, and square root of 16 is 4. And then 25 is, square root of 25 is 5. Okay, so let me just jot down those points. So I'm going to have a 0, 0, 4, 2, 9, and then 3. And then 25, oh no, 25 and then 5. But anyways, this graph is going this way. Okay, so you might want to memorize the graph of y equals square root of x, because that's one of the very basic functions that we use quite frequently. Okay, so let me just write this out as y equals square root of x. Okay, so if you know that you're going to have a horizontal shift of 4 units to the left, you can take each of these points that we just plotted and shift it over 4 units to just draw the new graph. Okay, so if I did it that way, then let me just go like this. Okay, so let's go with this point, 0, 0. So we're going to move this 4 units to the left. 1, 2, 3, 4. So that will be, where am I? 1, 2, 3, 4. Okay, now notice that the distance from here to here, do we have 4 units? Yes, we do. All right, now let's work on this point right here, which is 4, 2. Right, we're going to shift this point 4 units to the left. So that's going to give us 1, 2, 3, 4. That's going to be our new point. Let's check. Do we have 4 units in between? Yes, we do. All right, now let's take this point here, which was, what was it, 9, 3. All right, we're going to shift that 4 units to the left. So let me go 1, 2, 3, 4. Does it look right? 1, 2, 3. I think that's right. Okay, so again, the distance from here to here is 4 units. Okay, so our new graph is going to look something like, oh my gosh, something like this. And that's good enough. Okay, so our the pink graph is y equals square root of x plus 4. All right, but anyway, so what I did here was I did not use the chart. I just look at the graph and then just shift the graph over. Now, if you want to make the chart, and then if you just want to do the faster way, then just know that y value stays the same as the mother graph, but only the x values changes. Now, how much change? Well, this is going to horizontal shift 4 units to the left, so that means that you're going to have to subtract 4 from each value of x from your mother graph. So let me just do that. Y value stays the same. All right, and then we're going to subtract 4. So we're going to have, let me just write down, where can I write this? Okay, so let me just write down the values for the mother graph. We had 0, 4, 9, 16, and 25. And then we're going to minus 4, minus 4. Oh, goodness. Can you see this? So this is minus 4, 0, and then this is going to become 5. And then what is that? 12 more. And then 21. So where you need to plot the point is negative 4, 0, 0, 2, 5, 3, 12, 4, 21, 5. All right, now let's check to make sure that our argument is correct. So negative 4, 0, do we have that? Yes. 0, 2, yes, it's right. 5, 3, yes, this is correct. So this makes sense. Now let's go with the domain of G and the range of G. Okay, so let's first go with the domain of G. So now when you want to find the domain of G by looking at the graph, if you want to find the domain, you always look the graph from left to right and determine where the graph's going to begin. So if I look at this graph from left to right, the beginning point is at x equals to negative 4. Now remember, domain is the set of all x values, right? So in this case, our domain is going to be, let me just write it over here. settable x values such that x has to be greater or equal to -4. So that's in the set builder notation, and the interval notation is same thing as close bracket -4, and where does it go? All the way up to infinity. All right, so that will be the domain. Now let's go with the range. Okay, now again, when you look at the range, you want to look at the graph bottom upwards to determine where the graph begins, along what's the y value is. So here, our y value is where? What is that at this point? Which is 0. And then it looks like, remember, this tail end is going to keep going and going and going and going. Eventually, it's going to go all the way up very slowly. But so in this case, our range is going to start from y equals to 0 all the way up to infinity. So I'm just going to write it as settable y values such that y is greater or equal to 0. And interval notation will be close bracket 0, comma, infinity. And there you go. Yay, we're done with example 4. All right, so we just talked about the vertical shift and horizontal shift. Now what we're going to talk about is vertical stretches and compressions. Okay, so let's just, I already wrote the definition out just to save some time. So let's go. So it says, given the function f of x, a new function g of x equals a times f of x, where a is the constant, is a vertical stretch or the vertical compression of the function f of x. Now, there are 3 cases. It all depends on this constant a to determine what the function is going to look like. So let's take a look at 3 cases. Now, if a is strictly greater than 1, graph is stretched. Now, if a is strictly between 0 and a 1, like it's a fraction, like think of 1/2, 1/3, 1/4, then graph is compressed. Now, if a is negative, graph is a combination of vertical stretch or compression with a vertical reflection. So here, I already drew the graph just to show you what does it mean for the graph to be stretched or compressed. Okay, so let's take a look at our mother graph to be y equals x squared. So that's this red graph right here. All right, now let's look at our g of x. G of x is 2 times x squared. So our 2 is bigger than 1, so this will be case 1. So let's just observe the blue graph. So this blue graph right here is y equals to 2x squared, which is our function g of x. So what's happening is this. For the vertical stretch, for each x values, right? For each x values, the y coordinate of a point on the graph of g is 2 times as large as the corresponding y coordinate on the graph of f. So for instance, let's take a look at when x is 1. Oh no, can you see this okay? So I'm only looking at a graph of x squared, which is the red one, and then g of x, which is the blue one. Okay, so when x is 1, mother graph, your y value is 1. Now, 1 times 2 is 2. So that means that our graph of 2x squared, our g of x, your y value must be at 2 when x is 1. Now, same thing for when x is 2, our mother, I'm looking at the mother graph, that y value of the mother graph is 4. So what's 4 times 2? 4 times 2 is 8. So when x is 2, our g of x, the y value of g of x must be at 8, which makes sense. So this is at y equals to 8. Okay, so that's what's going on. So basically it's this, if you multiply by a constant, right? If you multiply a constant to 1/2 or even negative, what's going to happen is that your x value is going to stay the same, but you're going to have to either increase or decrease your y value by the value of a. So x stays the same and the y values are the one that's changing. All right, now let's look at h of x. H of x is 1/2 times the mother graph, x squared. So that's case 2. right? Because 1/2 is between 0 and 1. So that means that graph is compressed. So our mother graph is being compressed by 1/2. So let's just look at this green graph here. So this is the graph of 1/2 x squared. Okay, so let's argue in the same way. So let's just look at when x is 2, our y value is 4, right? So that means that our new graph, you just multiply the y value of your mother function by 1/2. So here our y value is 4. 4 times 1/2 is 2. So is x equals to 2, is our y equals to 2 on the graph of h of x? Yes. Does that make sense? And then now let's look at our p of x, right? So p of x is, I multiply by the -2 to our mother graph. So we have p of x is -2x squared. So that is this purple graph here. So notice that, do you see something here? Look at our graph, the blue graph. Which function is g of x? G of x is 2x squared. Now if I multiply by the negative, what happens? You take your g of x and then you just flip it over with respect to the x-axis. Now we're gonna be learning that in a minute, but anyways, if you multiply by a negative and by the constant, you're going to have a vertical stretch on the mother graph, but you're gonna have to reflect it along the x-axis. So just to summarize, so what is the vertical stretches and compressions? Well, when x is 2, let's just take x equals to 2, y is 4. So the vertical stretch by 2 means that your y value changes, and furthermore, you multiply the y value of the mother function by 2. So if this is 4, this point should be 8, right? So let me just make that dot. So this will be your vertical stretch by the factor of 2. Now, if I take the same point and then let's look at 1/2 x squared. So that means that you take the y value of the mother graph, which is 4, and you multiply that by 1/2. Okay, so that will give us 2. So notice that this is considered as a compression by a factor of 1/2. And these are your vertical stretch and compression. All right, here we go. Horizontal stretches and compressions. So given the function f of x, a new function g of x equals f of b times x, where b is the constant, is a horizontal stretch or horizontal compression of the original function f. Again, there are 3 cases. If b is strictly greater than 1, then the graph is compressed by 1 over that constant b. All right, now if b is between 0 and 1, the graph is stretched by 1 over b. So be careful here. So let me see. Our b is between 0 and 1, right? So think of it like maybe as 1/3. So if b is 1/3, then the graph is stretched by 1 over 1/3. So what's 1 over 1/3? That's 3, right? So basically, if your b is 1/3, then the graph is stretched by 3 units. All right, but anyways, let's take a look at case 3. If b is negative, then the graph is a combination of a horizontal stretch or compression with a horizontal reflection. So let's look at the same mother graph as when we learned the vertical stretches and compressions, which is y equals x squared. So that's this red graph right here. All right, let's look at our g of x. Now, g of x is, I wrote it as 2x whole quantity squared. So that's precisely, so this is exactly the same thing as f of 2x. So in this case, our value for b is 2. Okay, so that will be case 1 because 2 is greater than 1. So what does it say? If b is greater than 1, then the graph is compressed by 1 over 2 now. So let's look at the mother graph when x is 2. So that's this point right here. So we have 2, 4 right now. And now let's look at the graph of g of x. That's this purple-ish, bluish line here. Okay, so the horizontal stretches, compressions, your y value stays the same, but your x value is going to get changed. Okay, so furthermore, according to the definition, our mother graph better be compressed by 1/2 because I have a 2x squared. Okay, so in this case, you just take your x value and multiply that by 1/2. What do you get? X equals to 1. And then your y stays the same. All right, so that's what's going on here. So this point right here is 2 divided by 2. 2 times 1/2, same thing, so which is 1. And then your y value stays the same. So this will be your horizontal compression. Now let's look at h of x. h of x is 1/2 x squared, so that's exactly the same thing as f of 1/2 x. So in this case, our b is 1/2. So when b is 1/2, we're talking about case 2. So now what's going to happen is that graph is stretched by 1 over 1/2, which is going to be 2. So be careful right here. Okay, so let's see if that makes sense. Okay, so let's look at this green graph. That's our graph of h of x. Now let's take the same point 2, 4. All right, so again, horizontal compressions and stretches, your x value changes. Now let's take the x value of 2. And this is going to be stretched by the units of 1 over 1/2, which is by 2. So all you have to do is multiply 2 times 2, and then your x value is going to become 4. So this point here becomes 4, 4 now. So let me write that out. All right, and then this is considered as your horizontal stretch. So here's the summary that I wrote. If you do the horizontal stretches and compressions, all you need is to change the x value by the factor of 1 over b. All right, let's take a look at example 5. A function f of x is given by the table below. Create a table for part A, g of x equals 3 times f of x, h of x equals f of 3x, and then p of x is f of 1/3 x. Okay, so let's first go with g of x. So what's going on here? So g of x is 3 times f of x. So what do we got going on? We're going to have to stretch our f of x by 3 units, meaning that your x value stays the same, but your y values is going to get stretched by 3. Meaning that you're going to have to multiply each of the y coordinates by 3. So here, your x value stays the same, 2, 4, 6, 8. And then what you need to do here is you just multiply by 3. So you're going to have to go multiply by 3, multiply by 3. And then our new value for g of x is going to be 3, and then 9, 21, and then 33. Now let's go with part B. So part B is h of x equals f of 3x. So in this case, do you notice what's going to happen here? We have a f of 3x. So do we have a horizontal compression or stretch? This will be compression because our b is 3, which is greater than 1. So let me write that out. So this is the horizontal compression by 1 over b, right? So in this case, it's going to be by 1/3. Now for the horizontal compression, remember your y value stays the same, but the x value changes by the factors of 1/3. So I'm just going to copy down our y value. And then I'm going to take each x values and multiply by that by 1/3. So let me just copy down the mother graph, x values for the mother graph, 2, 4, 6, 8. So here I need to multiply by 1/3, 1/3, 1/3, and then 1/3. Then you're going to have, what do we get? 2/3, 4/3, 2, and then 8/3. All right, now let's do part C. P of x is f of 1/3 x. So please automatically recognize that we're going to have a horizontal, which one now? Yes, horizontal stretch by the factors of 3 in this case. I'm going to write that out. So this means that horizontal stretch by 1 over 1/3, right? So that's why this is stretched by 3 units. Okay, so again, your y value is going to stay the same as your the y values of the mother function. All right, and then all you have to do is multiply, let me see, 2, 4, 6, 8 by 3 to get the new coordinates for x. So it's going to have 6, 12, 18, 24. Okay, I think we're done with example 5. Okie dokie. Now what we're going to talk about is reflections. Okay, so ready? Given the function f of x, a new function g of x equals negative f of x is a reflection about the x-axis. And g of x equals f of negative x is a reflection about the y-axis. So I drew a picture here just to let you know what is the reflection about the x and y-axis is. So let's look at y equals square root of x. Please memorize this graph. Now let's first look at the negative f of x. So negative f of x is negative square root of x. So that's this case right here, the first case. Now it's a reflection about the x-axis. So basically what you need to do is you take the square root of x and you rotate that about the x-axis. So if I flip that over by rotating the x-axis, you're going to get the graph negative square root of x, which is this graph right here. Now let's take a look at f of negative x. So f of negative x is going to become square root of negative x, right? Now remember, square root, whoever sits inside of the square root has to be always greater or equal to 0. So that means that in order for this expression to exist, your x value has to be negative, because we have a negative times a negative that will give us a positive value. So that's why I wrote x must be less than or equal to 0 in order to make sense. Okay, so if we have that, then the statement says that you're going to have to reflect our mother graph, which is y equals square root of x, about the y-axis. So in this case, you're going to have to take your y-axis and then you just rotate it. Okay, so if I rotate the mother graph about the y-axis, then you're going to have a graph, this graph right here, which is the purple graph, which is square root of negative x, where x is negative. I know, so much information, right? This section is quite lengthy, so hang in there. We can do this, all right? So next topic is even and odd functions. So given the function f of x, here's the definition. F is an odd function if f of negative x equals negative f of x. Now, f of x is an even function if f of negative x gives you f of x. Okay, so let's do some examples. So example 6, determine whether the given functions are even, odd, nor neither. So let's do a few problems here. So here is our first f of x equals x squared plus 1. Okay, so again, let me just rewrite. We say that f of x is even if f of negative x equals to f of x. And then f of x is odd if f of negative x, it's going to end up negative times the original function f of x. Okay, so in order for you to check whether the given function is even or odd, what you need to do is you need to replace the argument of x with the negative x, and then you see the result. Okay, so let's just do this. So first, I'm going to check. So how do I check? Plug it in negative x in place of x. Then here what we're going to get is negative x squared plus 1, which is x squared plus 1. But what do you know about x squared plus 1? Well, isn't that just f of x? So after I plugged in negative x in place of x, I got the original function back. So I'm just going to write this guy as f of x. So what does it mean according to the definition? Well, we plugged it in negative x and then we got a f of x back. So therefore, f of x is even. All right, now let's take a look at the next one. Let's look at f of x equals x cubed plus 5. Okay, so let's check. What do? We just replace the argument of f with negative x. So now let's see. So this is same thing as negative x whole quantity to the third power plus 5. So that's same thing as negative x cubed plus 5. So the question is, does this equal to f of x? Meaning, is it even? No, because our f of x is positive x cubed plus 5. So I have a negative. So this is not an even function. Now let's see. Is this negative f of x? Aha, be careful. Because if I have to rewrite this, right, by factoring out the negative, then I'm going to have negative x cubed minus 5 in a parentheses with the negative sign out in the front. But the thing is, this guy does not equal to f of x, right? It becomes f of x if the middle sign is positive, but it's not. So this does not equal to negative f of x either. Okay, so therefore, it's not even, it's not odd, so our answer is neither. All right, now let's look at the next one. F of x equals x cubed plus 2x. All right, so let's check. Replace the argument of f with negative x. And we're going to have negative x, whole thing to the third, plus 2 times negative x. So this is same thing as negative x cubed. And then you're going to have a minus 2x. Okay, so first of all, does this equal to f of x? Does not even look like him, right? So it's not even. All right, now let's see. You got to go one more step. Factor out that negative and see what's going to happen. So if I factor the negative out in the parentheses, I could write it x cubed and then plus 2x. So now let's analyze. So is this negative f of x? I think so, because our f of x is x cubed plus 2, and that's exactly what I have with the minus sign on the whole entire front of it. So this is negative f of x. So in this case, f of x is odd. All right, example 7, let's play a completely different game than example 6. So example 7, graph the function f of x equals absolute value of x plus 3 minus 5 in steps. So first, what we need to do is come up with a basic function. Then we're going to do our shifting, stretching, or whatever we need to do in order for us to get absolute value of x plus 3 minus 5. So step number 1, my first function that I'm going to use is absolute value of x. All right, so let me just write it as, let's go with the first function. I'm going to start out with absolute value of x. All right, now let's look at the second step. So I'm just going to call it y sub 2. So now I could, what I need is absolute of x plus 3. Right? So if I call the first function to be absolute value of x, if I add 3 to it, do you remember what to do? So if this is f of x, then absolute of x plus 3 is same thing as f of x plus 3, isn't it? So in this case, what we need to do is we need to shift the absolute value of x 3 units to the left. So I'm going to write that out. So we're going to say shift left 3 units. All right, now let's go with the third step. So I'm just going to call it y sub 3. So now we have absolute of x plus 3 and then minus 5, right? So do you remember what to do? If I have a minus 5, you're right. We're going to have to shift the y sub 2 5 units downward, because this is the equivalent of saying y2 and then minus 5. So I'm just going to write it as shift down 5 units. And that is precisely our f of x that we want to graph. All right, so let's do it. Okay, so first let's go with absolute value of x. So if you have not memorized what the graph looks like, no problem. We could always go X and a Y chart. This is going to be absolute value of X. Oh my gosh, I can't even draw a straight line right now. All right, so let's see. We can go maybe -2, -1, 0, 1. Maybe that should give us enough idea. So then our Y value is going to be absolute value of -2, which is going to give us 2. And then absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. Okay, so we're going to have 0, 0. And -1, 1. And 1, 1. Is that right? And then what is that? -2, 2. Oh, I forgot to write 2 here, but you got the idea. Absolute value of 2 is 2. So here I'm going to have that. So basically, the absolute value function, it's going to look like a V. It could be looking upward, or it could be facing downward. So this is our function y1 equals the absolute value of x. All right, now let's go with y2. So we're going to take this graph and we're going to have to shift left 3 units. So take each of the point. So 0, 0, we're going to have to shift this point 3 units to the left. So what we're going to get is, let me see, 1, 2, 3. This new point is here. And let's take this point, which is -1, 1, shift 3 units. So that would be here. You got the idea, right? And then, let me see. When x is, let me see, 1 and then y is 1, we shift this point 3 units to the left. So we're going to have this point here. And then 2, 2, 2. All right, so 2, 2, if I shift 3 units to the left, this is the point that we're going to get. And then this is the point that we're going to get. So this is the graph of y2, y sub 2, which is absolute value of x plus 3. All right, now let's go with step 3. So step 3, we're going to have to look at y2 and then shift that graph 5 units down. So if I take this point here, I need to move that 5 units downward. So you got 1, 2, 3, 4, 5. So let me just jot that out. 2, 3, 4, 5. I just lost the point here. There you go. And then we're going to do the same thing to each point that we see. So this point is going to go 1, 2, 3, 4, 5. And then it's going to be here, here, here. Does that look okay with you? All right, so it looks like this is going to be our final graph if I connect those dots. So this is our graph. F of x equals absolute of x plus 3 and then minus 5. All right, let's look at example 8. Find the equation of the graph below. So first of all, this graph is in shape of a V. So that means that we're going to have an absolute value of x, and then we're going to tweak that by shifting up and down or left and right, stretch, compress, or whatever we need to do. So what I'm going to do is let's first start out with y equals absolute value of x. So here's the graph of y equals absolute value of x, but the graph that we want, we need to flip that over with respect to the x-axis. So in that case, what we need to do is you take y equals absolute value of x and then multiply that by a negative. So let's write every step out. So first function, I'm going to start out with the absolute value of x. Now, if I flip it over, then let's just call that y sub 2. I'm going to flip that over so that way we're going to have a graph that's looking downward. All right, so here's the graph of y2, which is negative absolute value of x. All right, so now let's see. The vertex, or the highest point on the absolute value here, I need to move that over to when x equals to 3, because that will be the highest or the vertex of the absolute value, right? So that means we're going to have to shift how many units to the right. So let's see. Here's 1, 2, and a 3. So first what we need to do is we're going to take our y2, which is negative absolute value of x, and then we want to shift that 3 units to the right. So that way the vertex matches up. So how do I write that? Remember, so let's just call that function y sub 3. So we're going to have to tweak negative absolute value of x. But the thing is, I need to shift it 3 units to the right. So that means I better have absolute of x minus 3. So this is by shift right 3 units. Okay, so then our vertex will be here. So let me draw that graph. And here it is. All right, now what else we need to do? Well, it looks like in order for me to get to the graph that what we want, we need to move this point how many units above? 1, 2, 2 units above. So basically we have to take this graph, which is y3, and shift the whole entire thing 2 units upward. And let's call that function y sub 4. So do you remember what to do if you want to shift y sub 3? So this is our y sub 3 up 2 units. That means that I need to add plus 2 to this whole thing. All right, so then let me just write this as shift upward 2 units. All right, so if I did that, then do you see that we're gonna have the graph that what we want, because this point is gonna go 1, 2, and this point is gonna go 1, 2, so it touches this. This point's gonna go 2 units above, so that is exactly what we want. So let me just write down the answer. So therefore, our function that we're looking for is negative absolute value of x minus 3 and then plus 2. So this is going to be our answer. Oh my goodness, how's your brain doing? Mine's pretty burnt out right now. But anyways, we learned so many things in this section. So what I decided to do is I'm just going to write down the summary sheet, which is here. So this is all the summary sheet for the transformation of graphs. So feel free to use this if you like. And also, I told you that you're gonna have to memorize some basic functions. So I also summarized that for you as well. So here they are. So these are some useful graphs to memorize. So first one is y equals x squared. It's a parabola. Absolute value of x, we talked about that. Y equals x cubed, square root of x, natural log of x, and then e to the x. And those are very, very common functions that you're going to have to know for our class. So please try to memorize that. Okay, so I'm going to end here. So great job. And if you have any questions at all, you know where to find me.